Let's start with a new chapter. 11 is called a tropical extratropical synergy. This is a really short but mathematically a bit intense, but the physics is amazingly cute, very interesting. We have talked about wave kinematics, interactions with the basic states, and we talked about how that translates into extratropical influence on the tropics, and then we looked at the tropical influence on the extratropics. Now we are going to combine that and show that actually there is a continuous exchange of something called potential vorticity substance between the extratropics and the tropics. And this exchange actually has a great role to play in maintaining the basic zonal state in the tropics. We are going to talk about the upper atmosphere with some reference to lower atmosphere, but essentially it's about the Hadley cell that's creating the divergence from the tropics, creating this westerly jet in the extratropics. The jet has this certain structure, for example, the westerly duct and the tropical upper tropospheric trough. And so the potential vorticity that we have talked about before obviously depends on diabatic heating and dissipation. What we will show is that we can create a quantity that's totally conserved between two isentropic surfaces even with diabatic heating and dissipation, and that one tends to be circulated between the tropics and extratropics with nearly zero cross-latitudinal transport. So whatever is coming in is going out, and yet there is some dissipation which affects the zonal flow. Okay, so this is the figure we had seen, the easterly jet, westerly duct, the westerly jet that is critical coming off of Asia, creating this outflow region, similarly off of North America with a weaker interaction with the tropics in the Atlantic. The Pacific, Eastern Pacific especially, has a great interaction happening between the extratropics and the tropics. The signature gets carried westward and then back into the extratropics. So we have some kind of a loop here that we will see that is really interesting. There are Rossby waves in the extratropics, of course, which are smoothly propagating, reversible in the case that they are just oscillating, so the entropy is conserved, whereas you have also situations where you have breaking Rossby waves which pump potential vorticity into the lower latitudes, as we saw the relation with the convective signatures in vertical flow and low OLR and so on. So we'll see that these non-conservative or irreversible processes are also important in terms of how the basic state is maintained. And these are what are called recurrent or recurrent processes, because there is always an eddy flux from the tropics into the westerly jet region, and there are always Rossby waves being created, and there are always Rossby waving intruding into the tropics. So this is not just one-off, it's constant energy and the creation of these tropical, extratropical exchanges. Let me leave that introduction there, but it's too short, so let me continue to look at the equations. As I said, the equations are a little bit hairy, but we will not derive all of them to focus on the physics again. But there are lots of references provided in the chapter that you can follow up if you're comfortable with the math and are interested in more details of what is being shown here. As I mentioned before, we will look at the mean and transient potential vorticity on the 370K isentrope, which is in the upper atmosphere. We are interested in the mass injection by the Hadley cell into the upper atmosphere, its meridional divergence, and the sinking in the extratropics. So we'll do a little bit of mass sourcing kind of calculation as well. If we look at the advection of the potential vorticity, the equation is something like this, where the sigma is this isentropic density, okay, and Q is our potential vorticity, which we had defined before. V is the isentropic flow field, which we can come back to later on in terms of geostrophic balances and so on. So we will try to see how the potential vorticity that is set by these processes of adiabatic heating and injection into the upper atmosphere are being circulated around. So we will look at that in the isentropic construct. So the potential vorticity multiplied by this isentropic density can be thought of as a potential vorticity substance. So it's not just the potential vorticity, but it has a unit mass associated with it, where again QS is minus eta theta, which is our total isentropic vorticity that we discussed before. So we can now write the advective component of the potential vorticity or the potential vorticity substance in terms of QS times V tilde, where V tilde has U, V, and 0. And this is on an isentrope between two isentropes. We will see that there is something called an impermeability theorem that emerges, which basically says there are no fluxes across the isentropic surfaces. So the cross isentropic term here is 0. Okay, this is how it looks. You have isentrope on pressure P1 and pressure P2. So we are going to mix a little bit here. You have the gradient d theta dp happening between them, and the potential temperatures theta1 and theta2. As you remember, theta increases with height. And you have two, the latitudinal direction and the longitudinal direction with the flow field V tilde on the layer between two isentropes. These are the isentropic isoplates Q1 and Q2. And there is a flux QSV with unit vector n tilde, which is perpendicular to latitude lines everywhere. So you are trying to, obviously you are interested in the meridional exchanges. So whatever the direction of flow on the isentropes, we are just going to look at the meridional components across latitudes, because we're going to focus on what is happening to the potential vorticity substance in terms of fluxes towards the tropics and out of the tropics. Okay, that sets up the problem. So the unit vector n tilde here is 0, -1, 0, so normal to the latitude line everywhere. And the zonal average of the flux is over a latitudinal circle, JA dot this unit vector times DL, which is the path along latitudinal line. Okay, we will see that with observational evidence, we will see that this basically turns out to be 0. We have to worry about other terms as well later on. But then we have to explain why that is, the physics of why the southward transport of the potential vorticity substance is balanced by the northward transport of it after it's being advected westward by the easterlies, after it being injected in the westerly duct or the tropical upper tropospheric trough, and then being brought back into the extratropics. Okay, very, very nice stuff. Again, just get comfortable with the equations, even if you don't know the derivations. When you look at the equations, the terms should make sense in terms of their physics, and then you should be able to explain the physics. That's most critical.